Okay, so this is the continuation of my video on Introduction to Reinforcement Learning. This is part 2, and this is going to be more of a formalism of, we're going to define what we need in order to do our first algorithm, basically. Okay, so in order to do that, we need to formalize our notation. And we have 3 main bits of notation. So little s at time t. Okay, so this is the state at time t. So we're at time t. Okay, so this is this. So it is the state. And capital script S is the state space. Capital script S is the set of all possible states. Okay. And then A sub t is in script A is the action of the agent. And script A is the action space, the space of all possible actions. Okay, and then finally, RT, which is equal to script R of S T, A sub t, and then the next state. This is the reward. Okay. And that script R is called the reward function. Okay, so that's the basic terminology that we need, and hopefully, yeah, you can read that. We have a state space, an action space, a reward function for a given environment. So time t, they would say in a given environment. We have these spaces and function that we need to consider. Okay. As I mentioned in the previous lecture, when an agent decides to take an action, the state space transitions to a new state, possibly an equivalent state, but it still transitions to a new state at a different time. So that's done by way of what's called a transition function. So environments transition from one state to the next by using a transition function. And this is more or less like a technical detail that we won't need for the algorithm that we're going to discuss, the first algorithm. But it's important that we learn all the terminology so that when we're reading about the algorithms, we can implement them correctly and have, again, a big picture, a high level interpretation of what the algorithm is trying to say. especially since a lot of times when you come across descriptions of reinforcement algorithms, they're admittedly very vague and they don't get into the details too much, but they say a lot of words that we're using. You need to be familiar with them in order to have, again, this high level interpretation of what's the big picture, what's going on, what is the agent trying to do. Now, this transition function again, it's going to be formulated, as I mentioned before, by way of a Markov decision process. I'll just write it out. So Markov decision process gives that the next state, which is so little s of t plus 1, is sampled from a distribution, a probability distribution of choosing, how did I do that? Of choosing state s of t plus 1, given we were just in state t and we made action t. So the states are, again, chosen from some probability distribution of this conditional here. Okay. So this is called the Markov property. And yes, every sequential step before here is going to somehow convey information to how the states transition. But it turns out that it's good enough just to look at the very previous ST, AT. We don't have to look back any further to get a new state when we choose it in this distribution here. Okay, so we should include that here as one of the properties that we have. So for a given environment, the Mdp formulation, so yeah, I'll just say Markov decision property formulation of reinforcement learning requires we have a state space S, an action space A transition function P, and a reward function R. If we have all of these things here, then we can formally define a optimization problem and an algorithm that would help us solve this. And again, we want to, as I mentioned in the previous video, we want to somehow maximize the rewards, where the rewards are taken over a trajectory of experiences, which are these triples of state, action, reward, state, action, reward. We want to maximize the rewards for our agent who is making decisions or actions in that environment. Okay. So let's go ahead and do that and look at what our objective is formally. So recall from last time that tau equals to state 0, action not me, reward not, dot, 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 state at time capital T, action at time capital T, reward at capital T. This is a trajectory for a given episode. Again, an episode is just a sequence of time steps from time is equal to 0 to a terminal state or to a maximum allowed time. For each time state, we have an experience, and a trajectory is just a sequence of experiences where we have state, action, reward as a given experience. So for a given episode. And again, we just use tau to typically denote that. So the way that we're going to measure our reward is with what's called a return. And the return is basically a weighted reward. And by that I mean, so that's not a script R. Script R will do like a curly, so this is a normal R. So the return for a trajectory T, we're going to say is the sum from I is equal to 0 to capital T of gamma, lowercase t there, gamma to the power T times the reward of T. And then here, little t is in the interval 0, 1. So that gamma is kind of like it's scaling the rewards, and it's mainly there so that to prevent from divergent series when t is like, when t goes to infinity, like for these episodes where it's not finite, if there wasn't a scaling factor in there between 0 and 1, then it wouldn't ever really converge to something that would diverge. So that's one of the main reasons behind that. But also, it gives a weight to the rewards. So because t is in the interval 0, 1, you can typically consider the open interval really. It's some ratio. So like if it was 1/2, so 1/2 times the first reward t0, and then 1/4, oh no, it'd be the first reward plus 1/2 times the second reward, so forth and so on. It gives importance to the rewards. It's weighting the rewards. So that's what it's doing here. And again, we need to do this in the case that we have infinite episodes. But other than that, just think of it as a scaling or a weighting of the rewards for each triple here. Okay. So then our objective function again, hopefully I'm not moving too fast. This trajectory, each instance in here is a triple. There's a state and an action made by the agent, which gives a reward. For a given trajectory, this is the return of that trajectory. It's a weighted sum of each of those rewards. And our objective function is going to be denoted by J, okay? And this is a function of the trajectories. And this is going to be the expected size of a trajectory taken from some distribution of the rewards of a trajectory. So recall that the state transitions was, they were taken from some distribution, this probability distribution over here. The rewards, each action that we take for our first algorithm is going to be chosen from some probability distribution. So since it's not deterministic, the returns are going to be different for the same probability distribution. They could be different, right? But among like all of them, if you average them out, that's what we want our objective to be. So we want, in the end, to maximize this expectation, the average rewards for a given trajectory. Okay. Now, that being said, let's go ahead and let's look at some pseudocode that would kind of model this Markov decision process formulation of reinforcement learning. And once you see that, I think that it'll become a little bit more clear on how we're going to start trying to kind of implement this. I'm going to pause the video and erase, and then we'll talk about it. Okay, so I've gone ahead and wrote out pseudocode for the general Markov decision process control loop that will be used in quite a few of the reinforcement algorithms that we learned. So the only thing that we're really missing here, which when I say only thing, there's quite a bit, but the main thing we're missing is the optimization part, where we want to maximize the objective. So let's talk about what's in there. The code is going to be similar, not exactly, but similar to what you would see in Python, where we have E and V is the environment, and agent is given. So E and V and agent, environment and agent, and these are, you can think of these as classes with methods and everything that you can think of when you think about Python classes. So for each episode, so an episode again is a sequence of experiences here. We're going to start the state over. So the environment, we're going to reset it. We're going to reset the agent, and then we're going to begin play. And the maximum amount of time we're going to allow is capital T, as before. And we're going to take an action, which is given. The agent has an action method, pass in state, it'll make an action. Okay. Once we have an action, we give that action to the environment, and the environment takes a step according to that action and returns a state and a reward. So this is like your ST plus 1, that's your ST, there's your reward, and there's your AT. Okay? So once you have your state reward, you have action, state, reward. And so this is the previous, so it's an action, that's the previous state, even there. We update these things. If we've reached a terminal state, we break out, end everything. Otherwise, we go back up to another episode. We reset our state, reset our agent, and then do this again, collect the information, observe what's happening. If environment done, we break. Otherwise, come back up here, another time step, keep on going. I think I misspoke for a second. This if statement break is inside this for loop. So if you break out, then you go up to the episode. But you're going to continue every episode that's listed there. Okay. So we have an objective here. We have a return function. We have a general outline of how this should go, which, by the way, you can go ahead and do this on your own, where you just pick a random action and give that action to your environment and just see what happens, right? And you don't even need to consider an agent, just give the environment random actions, it'll just return states and rewards, and that's one way that you can play with these environments that you can access through this OpenAI API, which I'll discuss in a minute. So this is the general idea. So now, nothing in here says anything about learning. Nothing over here says anything about learning. What should we learn? What should the agent learn? Well, there are three things that we can learn. The first is a policy. Again, recall that a policy is what, so given a state, the agent is going to choose an action, right? So a policy, yeah, so it's a function. So it's this, which maps state at time t to an action at time t. So we can learn the appropriate policy. And this is going to be stochastic. This in general is not going to be deterministic. So we're going to choose these actions from some distribution given a state. Another thing that we can learn is a value function. And there's two main ones. Two main ways to assess value. Let's see if I can fit it here. So there's V superscript pi for a given state S, which this is the expected return given state S. So we set S0 equal to the state that we're in, and the trajectory is taken from some distribution, sampled, and we want to look at the expected reward given that we're in that state. This again, time is equal to 0, capital T, gamma of T, and then reward of T. So this is how good or how bad your current state is on average. That's what this is saying. So maybe I should break it down. How good or bad a current state is on average. Okay. So that's one value function. Another one would be, another one would be, say, don't want to erase that yet. But it's called Q. So this is another value function. So this is now defined on a state action pair. And this is the expected return. So now we're looking at a state S and an action A, and a trajectory taken over some distribution of the reward. Again, so T is equal to 0 to capital T. So this here now, where's my yellow? This is imagining, so this is the expected return of taking action A given state X. Oh, not given. Taking action A in state X. So actually, a lot of times when you'll search maybe reinforcement learning online, you might come across something called Q learning. There's your Q function, and that's basically learning that function to optimize your rewards. It's another value function. So these are value-based methods. Number one here would be in the realm of what are called policy-based methods. Policies versus values. And then I need to mention a third thing that we could possibly learn, but we won't touch on in these lectures. The third thing that we could learn is the transition function. Now this, I honestly don't know much about, but it seems very intriguing to me that if we learn the transition function, which again is this probability of choosing, so the probability of state T plus 1 given A T, if we learn how the environment changes, right? This is telling us how what the next state is, right, in the environment. This is like, if we're able to learn the transition function, I imagine that to be like predicting the future. Like, if you know this, you know what the state is going to be like after you make that action in that state. So this is like equivalent to saying like, if you learn that, you're like imagining the future, which can be like incredibly useful, right? Like if you can predict what's going to happen next, what the next state is going to be, and I think that the researchers at DeepMind, when they did AlphaGo or Alpha something, one of those game playing reinforcement learning algorithms, they mixed learning the transition function together with a tree search and policy learning, which that is an active area of research. Is we have three things we can learn. We can learn a policy, a value, and the transition function. You can look at combinations of those learning, and you can put them against each other. You can use them together. Mixing and matching learning on these three things is where the state of the art is, I think, in reinforcement learning. So with that being said, just know that if your agent is learning the policy, these are policy-based methods. If your agent is learning the value, these are value-based methods. And you can mix and match value and policy-based methods with transition function methods and do some really amazing things. Now, for our purposes, especially for my machine learning students, we're going to now talk about a policy-based method called the policy gradient. Well, these would be policy and gradient methods. In particular, we're going to learn an algorithm called reinforce. The next algorithm you might learn will probably be maybe Q-learning, but for now, I hope to get through reinforce a policy-based method in the next video. So I'm going to stop this video and then we'll get started.